right, folks, so let's get started. My goal today is to finish chapter 8. And we'll start when we finish chapter 8 today, we'll start chapter 9 next week. So keep that in mind when we finish chapter 8 today, that the chapter 8 homework will be due on Sunday at midnight. All right, great. All right, we are talking about solution chemistry. So last class we talked about, hey, if we dissolve certain solutes in water, what they look like when dissolved in water on the particulate level is a little bit different. Sometimes there's ions present. Those are with things like strong electrolytes, ionic substances, or weak electrolytes. And then we have this idea, hey, we can still have covalently bound molecules dissolve in water, like sugar or glucose, but they do not split up into ions, that they stay intact as neutral molecules, and those types of solutions, non-electrolytes, do not conduct electricity. And so we looked at those different things there. So this whole idea of chapter 8 is we're dissolving stuff in water. So we have a solute and the solvent. So we need a way to kind of numerically describe how much solute we are dissolving in water. So what we see, and for the most part, we're talking about dissolving stuff in water. So in this picture, you see we have varying amounts of solute dissolved in these different vials, and it just so happens that this solute is blue. And so you can see on this side we have a lot of particles of that blue compound, so it's a very concentrated solution, and on the other side you see it gets a fainter blue. This is very dilute. So as chemists, we typically use the unit molarity as a unit of concentration. Concentration is just a way for us to convey how much solute are we dissolving in a set amount of solvent. So you can kind of think of like, you make Kool-Aid at home and you have like a concentrated mix versus a not so concentrated mix. The concentrated mix has not as much water, right? Versus the more dilute version, the less concentrated mix has more water within there. So with the unit of molarity, this is kind of a little bit of a throwback to our idea of dimensional analysis and looking at the unit derived units in this case. So our unit molarity, which is denoted by this big M, what that means, if we talk about like something has a 2 molarity concentration. Molarity means moles of the solute over liters of your solution. So just like when we say something, we're traveling at 6 meters per second, 60 meters per second. In 1 second, how far do we go? 60 meters. So this same idea here with molarity. In 1 liter of solution, we have some amount of moles of solute. So for example, if we say 2.5 molarity sodium chloride, we are trying to convey a concentration. In this case, it's 2.5 molarity. Recall what the unit of molarity is. It's moles per liter. So what 2.5 big M means, if you rewrite it, because I always forget what big M means, and so I just remind myself, okay, that big M means moles per liter. It means 2.5 moles of sodium chloride per 1 liter. That's what that means, moles per liter. So I always like, when I see a big M concentration, I always like to rewrite it so I actually know what it means. And so you can see here from the unit, we can write an equality based upon, if we want to do dimensional analysis, which we will do in a couple slides. So we can write the equality, 2.5 moles of sodium chloride equals 1 liter of solution in this case. So depending on, how we want to do our conversion, we can use that equality to get to any unit, either moles or volume, whatever we want there. So I really urge you, when you see the unit big M, molarity, just remind yourself, it means moles of your solute over 1 liter of that solution, because the big M doesn't really convey what it actually means. So just remember, molarity, moles per liter. So let's calculate the molarity of sucrose or sugar in McDonald's sweetened iced tea. All right, so I gave you some information here. I tell you that there are 54 grams of sucrose. and there's the chemical formula of sucrose in 30 ounces of sweet tea, which has that volume. And we want to calculate the molarity. So my strategy here is I ask the questions asking for molarity of sucrose. So what's the unit of molarity? What's the unit of molarity? It's on the previous slide. Moles per liter, all right? So this is my strategy here. Okay, it's asking for molarity. It means moles per liter. All right, so specifically, since it's asking for moles of sucrose, we should ask ourselves, when we set up this equation, we want moles of sucrose over liters of the solution that we have. So let's just take a look at all of the data that they give us. So they give us grams of sucrose, and they give us the volume, 0.89 liters. So that means to plug in numbers, right, to get the molarity, we need to plug in these numbers. I already know the denominator, right? We already know the liters, we know the volume, that's given. Liters of solution is given, it is 0.89 liters, we have that. But what we don't know is how many moles of sucrose we have. What does the question give us, though? It gives us grams. So how can we go from grams of a substance, of a pure substance, to moles of a pure substance? Molar mass, yeah. So I don't straight up give you the molar mass in this question, but what do I give you? The formula. So we can go ahead and calculate it ourselves using the periodic table, all right? So this question isn't just as straightforward as, okay, you know, one number divided by another number. We got to do a little bit of manipulation, which we can see from the unit of molarity itself. So we need moles of sucrose. Unfortunately, we're given grams of sucrose, all right? So I need molar mass in this case of sucrose. So let's just go ahead and do that to get molar mass. So there are 12 carbons, there are 22 hydrogens, and 11 oxygens. So I need to add up all of the molar masses of those individual atoms. Where do I get that? Okay, very good, very good. All right, so 12 carbons times 12.01. 22 hydrogens, and that's times 1.008. And then 11 oxygens, that's times 16.00. All right, and then you just add all those values up. And did I write it down? Am I good? Did I write it down? Yes, I did. All right, so if you add all those numbers up, you get 342 I'm just going to round it, 3. So when we use the numbers off the periodic table, what unit is that in? Grams per mole. All right, so the unit, the 300 number here, this is 0.3 grams per mole. Again, I like to rewrite these derived units to showcase what two quantities are they relating. So this value means that for every 342.3 grams of sucrose, that is equal to 1 mole of sucrose. So this is the number that we will use. This is the molar mass. This is the molar mass that we will use to convert the gram amount that's given to a mole amount. So this step is the same idea from, I don't know what chapter was that? Chapter 3? I think it was the end of chapter 3. We looked at gram to mole conversions and mole to gram conversions. So it's a throwback to that. But now we're just taking that idea one step further and thinking about, okay, how many moles of solute is dissolved in a certain amount of solution in this case. So I'm going to go back to that gram amount that they gave us. It's 54 grams. So where am I going to put the 342 gram? On the top or the bottom? Bottom. So 342.3 grams of sucrose is 1 mole of sucrose. So then just stick that into your calculator, and you get that 54 grams is 0.15776 moles of sucrose. Is that my answer? It is not, because what is the question asking for? It's not asking for moles of sucrose, it's asking for molarity. So to get molarity, remember, molarity is moles per liter. So we need to do one more step, and that is to divide that number we just got by the volume. And so what's that volume? the 0.89, all right? So I'm just gonna take that value. This should be rounded to 2 sig figs, but sometimes I get lazy. And so I just divide that number by 0.89, 2 sig figs as well. And so you see here, moles per liter, and this should give us our molarity. And I think, so our answer is rounded to 2 sig figs, so the answer is 0.18 molarity. I like to always say what the solute is after the concentration. So it's 0.18 molarity sucrose. I just like to say what it is, so there's no confusion about what we're talking about. All right, so see how I did that? So again, when you read questions like this and I give you a bunch of information and it says, okay, calculate the molarity of the solute, just remind yourself what molarity is. It's moles per liter. You know how to get moles of things, and then hopefully the question gives you liters in some capacity, and then that can, those are the steps to kind of put these pieces together. All right, so there we go. That is the molarity of sugar in sweet tea. So there's a lot of sugar in it. All right, here's another example. So how are solutions made? When we think about making that sweet tea, if I asked you, given that information, if you wanted to make 30 ounces of sweet tea, you know that there's 54 grams of sugar in sweet tea. I think most people would think you would take 54 grams of sugar and you would add 30 ounces of water. Is that what you think? That's how you think you do it, right? To make a sweet tea solution based upon the information there. So that's not exactly how we make solutions. Because note here, when we look at the unit of molarity, it is moles of your solute over liters of your solution as a whole. So when we add 89 or 0.89 liters of solvent, of water, that's not of the solution because the solute has its own volume itself. So to kind of get around that, how we make solutions in lab is first we weigh out the solute that we are focusing on. So in this case, it's sodium hydroxide. We want to weigh out 1.5 moles of sodium hydroxide. That ends up being about 60 grams. All right, and those are related by the molar mass of sodium hydroxide. So when we want to make a solution, in this case of 250 milliliters of solution, so what the important detail here, and it's a subtle detail, once we have that volume of, that solid sodium hydroxide in this flask, we don't measure 250 milliliters of water and add it and mix it. We don't do that. What we do instead is we use what's called a volumetric flask. And so instead, what we do is dilute with water up to a line that indicates that the total volume is 250.0 milliliters in that case. So what we're seeing here in this volumetric flask is the total volume of the solution being 250 milliliters. And so that volume includes both the volume of the solute and the solvent in that case. So you can't just add 250 milliliters of water because that's of the solvent. And so that's just a very small, subtle detail there, that the mass that you see here includes both the solvent and the solute, that the solute that we add, it has a volume in itself. So let's just go one step further here and let's calculate the molarity of this solution given this information. So again, how I like to start molarity questions is I ask myself, what is the unit of molarity? Moles per liter. But in this case, it's moles of what? Moles of what? NaOH. That's what the question's asking for. It's moles per liter of solution. All right, so that's just to be really, really specific here. So if we go through these values that are given, how many moles of sodium hydroxide are in this flask? 1.5. 1.50 moles of sodium hydroxide, and then the total volume is 250 milliliters, but we need to convert that to liters for this actual calculation. So I'm going to divide, by 1,000, 1 liter. So this is 0.250 liters. So that will be my denominator, the volume in this calculation. So 0.250 liters. All right, so looks like we're rounding to 3 sig figs here. And so my answer will be 6.00 molarity NaOH. And so note here about sig figs, if you put this into your calculator, if you do 1.5 divided by 0.250, your calculator will just say 6. But remember, we need to be smarter than calculators and recognize, hey, we have to convey significant digits in this case. Since both values have significant digits, 3 of them, our answer needs to have 3. So 6 is not the correct answer, it's 6.00 in this case, because those zeros are significant, so it is not just 6, because that just indicates 1 sig fig. All right, so there are some molarity calculations. There's basically 2 different ways I can ask you these questions. Either I give you a gram amount of your solute, or I give you a mole amount of your solute, but I have to give you the volume of the solution as well. And so with that information, you should be able to calculate molarity. If I give you the gram amount, I typically have to give you the chemical formula of the thing as well, because you have to be able to convert that into moles. So you can plug that into the molarity calculation. All right, so kind of taking it one step further here, we can actually use molarity as a conversion factor, and I kind of already showed you this already. When we are given a molarity value, so 0.65 molarity kBr, we can rewrite this into an equality. And again, if you just remember, what is the unit of molarity? It's moles per liter. So what this means is 0.65 moles per liter of kBr. So we can rewrite this molarity value into a conversion factor that can be useful for us. So just like all derived units, the number goes with the top unit, and then the bottom unit gets an implied 1. So what this value, molarity value, means is that there's 0.65 moles of kBr in 1 liter of solution. So that is a conversion factor that I can use. All right, so in this question, it's asking how many moles of kBr do I need to make 1.5 liters of solution. So my goal is to go from liters to moles of kBr. And thankfully, looking at the molarity value here, we can use that as a conversion factor to get exactly what we want. All right, so I like to start with the value that's given in this case. So it's 1.5 liters. Next, I use my molarity value in this case. So do I put the 0.65 moles on the top or the bottom? Top, yeah.
I had a sincere question.
Sincere.
How's this going to help me in the real world? Because I'm trying to become a dark Sith Lord. Like, I'm a Star Wars fanatic, and my dream is to become a dark Sith Lord. So I was wondering how is this going to help me in my real world? Anyways, can we continue to look?
Yes, thank you. Yeah, no, units can send us to outer space and being able to.
I'm sorry, I hate you.
Yes, can you please leave the classroom? Thank you. Can you please leave?
Yeah, I'm leaving right now.
Okay.
I'm just going to follow my dreams. I'm going to be like Disney on Ice, but ghetto.
Okay, all right. I'll just take you out. Let's just. All right. Can we leave?
Yeah.
Yeah, let's.
I'm like Disney on Ice.
That's great. I really appreciate that. Let's go out the door. Okay?
Am I cool or what?
Sure.
I'm sorry.
It doesn't sound like you're sorry. All right. Goodbye.
Have a great day.
All right. That was fun. I honestly think just, playing with units can really help us in life. All right? And recognizing that. All right? And so hopefully you can see that. Okay, that was a first for me. Okay. Did I do it? Thank you. Did I do okay? Okay, thanks. Okay. He did look, I never recognized him before, and so, all right. Where were we? Okay. We put the moles on top. Very good. Very good. All right. 0. 0.65, it goes on top because we want the liters of solution on the bottom. And I really hope that this looks super familiar, right? Like, as long as you have the whole idea of how to manipulate units, if you have a very strong understanding of units, you see that all these questions are basically the same. You know, and we're just trying to cancel units, all right? So what we see here is when we do this, liters cancel and we are left with moles. And I think that's our answer, right? What's our answer? We want moles of KBr, and so in this case, you do that math, it's 0.975, this should be 2 sig figs, moles of KBr. All right, but let's pretend this question, it didn't say how many moles of KBr is required. What if it said how many grams of KBr is required? What would we have to do? Use the molar mass. So we still do the exact same steps. We just go one step further and use the molar mass of KBr to get grams. So you go through the exact same steps. So just for fun, why don't we do that? If I tell you that the molar mass of KBr equals, I think it's 119 grams per mole. All right, we take this value that we just got, and to get to grams, we just use the molar mass value here. So 1 mole of KBr is equal to 119 grams of KBr, and I think there will be about 120, or no, it's like 116, but we want to round to 2 sig figs. All right, 120 grams of KBr in that case would be used to make this solution. All right, so those are 2 other ways I can ask you these questions. And really, on this slide, it's very similar to the previous slide, right? In the previous slides, I gave you moles and liters, and you had to calculate molarity. In this example, I give you molarity of volume, and you need to calculate amount of moles or grams in this case, right? So it's just kind of manipulating units here. All right, so that is concentration. That's concentration with the units of molarity. And I will admit, molarity is a hard idea to get your head around. All right, it's just a big M, and it means moles per liter. In my head, I don't really know how much a mole is. So here are other more common concentration units that you will encounter, especially in the medical field, or even if you just look at like nutritional labels and stuff. These are the types of units that you will see. Percent mass, or so percentage by mass, or percentage by volume, and a really, really common one that you will see is percentage by, percent by mass over volume. So what all of these percentages mean is, so percent by mass, we're still thinking about, okay, how much solute are you dissolving in your solution? So all of these kind of follow the same principle. Percent by mass, you are taking your grams of your solute and thinking about, okay, how many grams of solution do you have? And typically how you calculate that is you just take grams of your solute over grams of your solution times 100. All right? But the notion here, and I kind of mentioned this before, okay, solute and solution. Where, if we know how many grams of solvent we have, does that go on the bottom? Does that go on the bottom? Yes, but kind of, because remember, grams, the mass of your solution, the whole solution, it contains both the solute and the solvent. So keep that in mind, and I'll look at it, we'll look at an example here. Actually, let's just do one right now. Let's say I dissolve 5 grams of ethanol, and I add it to 20 grams of water. I just mix those 2 things together. Which one's the solute, which one's the solvent? Sorry, yeah, which one's the solute? The solute. It's right there. The 5 grams of ethanol and 20 grams of water. Which one is the solute? Why is ethanol the solute? It's the smaller one, right? Okay, all right. So if we mix those 2 things together, how many grams of solution do I have? 25 grams. all right? Because you mix both of those things together. So note here, ethanol, you guys just said, is the solute. So that's going to go on the numerator, but the other component, 20 grams of water, that's your solvent. So to do this calculation, if we wanted to do percent by mass here, this one, we would not do 5 over 20. We would do 5 grams over 25 grams because that's the grams of your solution. So this is equal to your grams of your solution. So I guess to actually write out a definition here, your grams of your solute plus your grams of your solvent equals grams of your solution. And a common mistake is that students will just assume that the solvent mass or volume or whatever is equal to the mass of, or volume of your solution, but that's not correct. You have to consider the volume of both. And we'll look at some examples here. All right, okay, so and that whole idea is within that denominator there, and we'll look at some examples. All right, percent by volume, same exact concept, but instead of grams of solute, grams of solution, it's volume and volume. So that's the big difference. And I'll note here that this whole idea, also the idea that your solvent and your solute equals your solution. So in this case, when we're talking about percent by volume, it's your volume of your solute plus your volume of your solvent equals volume of your solution in that case. So let me just write this, because I don't like words, I like equations. So I'll put, typically we're talking about milliliters. So if you have milliliters of your solute, milliliters of your solution, times 100, that is how you get your percent by volume. And then the last one here, and I think that one's the most common, is mass over volume. And the reason is when we think about solutes and like dissolving stuff, typically the things that we dissolve are solids. Is it easier to weigh a solid or find its volume? Weigh it, all right? But when we think about solvents, we think about liquids, right? Is it easier to weigh liquids or measure their volume? Measure their volume. So this is why mass over volume is a more common unit that you see in the medical field, because solids, easy to weigh. Liquids, easy to measure their volume. So that's why in this case we have mass of your solute, typically in grams. This should say grams. Or sometimes you'll see milligrams as well. So it's grams of your solute over milliliters of your solution, and then times 100. All right. So that's how you calculate that. And I'll show you how to do some of these calculations here in a minute. All right, so we got gram, milliliter, milliliter, and gram over milliliter. And the whole, the big idea here is the solute is always on the top and the solution is always on the bottom. Yeah. You should, if I say, hey, you have something that is 5% by mass something, you should know what this means. You should know that 5% by mass means that 5 grams of solute equals 100 grams of your solution. That's what you should know what that means. Solute. But so do you have to memorize that? Kind of. Because this would be different if I said, hey, you have something that's 5% mass by volume. Then this equality actually changes. It's still 5 grams of solute, but it's equal to what? Not 100 grams of solution, but instead 100 milliliters of solution, because you have a volume unit here instead. Got it? Yeah, okay, so let's look at some, do I have an example? Okay, just one kind of side one. So note here, I just said when we look at those like mass to volume units, when I said like 5% mass by volume, what that means is 5 grams of solute equals 100 milliliters of solution. So that's how we can turn that concentration into an equality, just like we did with molarity. So note here that the one side of the equality says 100 milliliters. So 100 milliliters is also equal to a deciliter. All right, and so oftentimes in the medical field, and don't ask me why they do this, they will report concentrations as milligrams per deciliter, but it actually means the exact same thing as percent mass over volume. It actually means the exact same thing, but that's the unit that you will see. So whether you see milligram over deciliter or you see percent mass over volume, those two, the calculations will be the exact same. I just wanted to point that out because if you ever get to your blood taken and you get your cholesterol measured and they tell you your cholesterol levels, those measurements are taken in milligrams per deciliter. And so I looked up normal ranges for cholesterol, for example. So LDL cholesterol, that's the good cholesterol, right? It's the low density lipid. Versus HDL cholesterol, that's the bad cholesterol. High density lipids, these are like healthy human ranges for cholesterol. Note here how it's in milligrams per deciliter, but it's equivalent to percent mass over volume as well. So that's just kind of a side note. We will be mainly working with these percentages. I just wanted to point that out there for you medical people, folks. All right, so let's do some practice problems using these percentages. And do note, when I give you a percentage, I have to give you what type of measurement it is. So in this case, W means mass. I'm sorry, that I should be more consistent. W means weight. So the same idea of mass. This is mass over volume. In this case. So I'm asking in this question, how many grams of NaCl is required to make 2.6 liters of this concentration of NaCl for a IV bag, so intravenous, those saline bags? How much salt do we need? So just like when we did molarity, I always like to write out the equality of what that concentration unit means. So 0.9% weight over volume means that there is 0.9 grams of what? What substance? NaCl equal to 100, what unit? Milliliters. Why milliliters? Because it's weight over volume. Weight over volume. So this is 100 milliliters of solution. So if I wanted to make 100 milliliter solution, I would have to put in 0.9 grams of salt. That's what this means. Okay, so that's how these percentages work. And so look, that's an equality that I can use to do dimensional analysis and get what I want. So we will use that, we'll put that to the side, and we want to go from the value given here is volume, 2.6 liters, and my goal here is to get to grams. So I'm gonna start with the value given, 2.6 liters, multiply by something. So note here, the unit given within our concentration is in milliliters, but I'm in liters. So I need to convert that to milliliters, this value into milliliters first to get them to match. So 1 liter on the bottom, 1,000 milliliters up top, and then keep going. So next, I'm going to use the 100 milliliter value here within the equality. So does that 100 go on the top or the bottom? What? Bottom, yes, I heard both. So you put 100 milliliters on the bottom. And then up top goes 0.9 grams of NaCl. Right? And that's it, because the question's asking for grams of NaCl. That's it. All right, and what's the answer? 23.4 grams. So what should I have for sig figs? I'm going to say it's 3. This should really say 0.90%. I'm going to say this is 3 sig figs. So 23 grams of NaCl. Okay. Yeah. So I think it's the idea, so when I said, so if I say something like, how about let's just do one more. Let's do one more, all right? And I think you'll see it. So it's all based upon this idea of can you write out the equality of the meaning of this concentration unit? So let's look at this next one. It's still kind of the same thing. Milk fat is measured in percent mass, percent by mass. All right, so 2% milk is 2% fat by mass. So let's rewrite that concentration into an equality. So just like when we said 0.9% mass over volume is equal to 0.9 grams equals 100 milliliters, if we do the same thing here, 2% mass over mass means it's 2% fat. So what the solute in this case is fat. So 2% here means that 2 grams of fat equals 100 what unit? Grams? Are you sure? Yes, because right here it's percent mass over mass. So see how the denominator here is mass? So it's 100 grams of what? Solution. What is the solution? Milk. Yeah, so it's 100 grams of solution, or in this case, it's milk. So for every 100 grams of milk that you, 100 grams of milk that you drink, you are also drinking 2 grams of fat in this case. Yeah.
Wouldn't you have to divide the percent by 100 because it's grams of solute over grams of solution times 100?
So I'm cheating a little bit right now. You can divide it to make it a fraction, and I promise you it'll be the same exact thing. So I'll show you right here. So 2%, if we turn that into a fraction, you said you divide by 100, right? So it's 0.02. Okay. So recall the definition for percent mass over mass. It's mass of solute over mass of solution. So for 2 grams of fat, in this case our solute, over 100 grams of solution, it's the same number. You see it? Yeah, so doing it this way, just always implying that the solution is 100 grams, kind of gets you around it. Or if you think about this, if I say that you have a whole bunch of M&Ms and 5% of them are blue, right? For every 100 M&Ms I give you, how many of them will be blue? 5. So you can say 100 M&Ms equals 5 blue M&Ms. So that's, when we think about percentages, it's a way we can kind of cheat and get around it, get around fractions, because I hate fractions. Yeah. Is that why you were confused? Yes, yeah. So this is the way we can easily make the equality. Do you see it now, kind of? Okay, yeah. Exactly, yes, exactly. Because in this case, if I say 5% blue M&Ms, you know that for every 100 M&Ms, 5 of them are blue. If I say you're drinking 1% milk, so mass over mass, that means for every 100 grams of milk, 1% of it, or sorry, just 1 gram of it is fat, because 1 gram over 100 grams is 1%. Yeah, okay, all right. Okay, so let's actually do this question. So here is our equality that we are working with. So what do they give us? We want to know how many grams of fat there are, and here's the total mass of the milk. So 3.9 kilograms of milk. All right, but look at the equality that we are starting with here. All right, so we need to convert that kilogram into grams. All right, I forgot what chapter all those conversions was. Maybe chapter 1? Yeah, so those are all coming back, So 1 kilogram on the bottom, 1,000 grams of milk on the top. Now the idea is we can now use the concentration unit. Where will the grams of solution go? Top or bottom? What, but both of them are grams. Both of them are grams, aren't they? Yes, it's solution. Yes, very good. This is grams of milk. So this is 1,000 grams of solution. You guys are so bright. So then it's 100 grams of solution or of the milk on the bottom, 2 grams of fat, which is the solute up top. And so what's the answer? 58 or 78? 78 grams of fat. Geez, wait. What's this? A gallon of milk has 78 grams of fat in it. The whole thing. My husband drinks like a whole gallon like every 2 days. It's gross. Yeah. I'm lactose intolerant, so I don't even drink any. So. All right, that's gross. All right. No, but he drinks skim milk. So never mind. So 2%. I grew up on whole milk. Geez, I can't even imagine how much fat is in that. Geez. Okay. All right. How do we feel better about those percentages? And it works exactly the same. Even if we did volume, percent volume over volume, it's again, volume of the solute equals 100 milliliters of your solution in that case. Okay, so how else can we think about concentration? So does anyone ever drink orange juice like this? You do? Yeah, you get it from the freezer aisle, you dilute it. So I had a hard time finding a picture that actually had the directions of how to make this, this orange juice. So if you don't know, you buy this in the freezer aisle, you throw it into a pitcher and you dilute this frozen orange drink with water, right, to make like ready-made orange juice. And it's better than the powdered stuff, I would definitely say. And so if you look at the directions here of this frozen orange juice concentrate, it says to take the whole can of the orange concentrate and you dilute it, or you add 3 cans of water. 3 cans of water. So if we think about a pitcher, all right, we have a pitcher of and we're making this stuff. You throw the orange juice in there, right? Or the concentrate, and then you add 1 extra can of water, 2 extra cans of water, 3 extra cans of water. So in doing that, you increase your total volume to 4 times what you originally had, because you're adding 3 extra cans here. And so this is the idea of a dilution factor, all right? That once you are done making your orange drink, you have a total of 4 cans worth of volume there, but you started with 1 can because you added 3 cans of water. So water in this case would be the solvent. Here is your solute. You're making a final volume, final solution volume of 4 cans worth. So we say that the dilution factor is 4 in this case. So it's kind of weird saying like, okay, you start with 1 can of your orange drink, you add 3 cans of water, and so that's why you have a total of 4 at the end, and that's why the dilution factor is 4. All right, so that's kind of another way we can think about concentrations. Probably the more common way we do calculations concerning concentrations and dilutions is if you took chemistry in high school, you might have heard the equation M1V1 equals M2V2. Yeah, maybe. It doesn't, if you haven't, it doesn't matter. We'll learn about it now. This whole idea that you can take a solute, a solution, with a certain concentration and dilute it. When we dilute something, we just add water. So when we add water to a solution, do we change the amount of solute that we have? No, we're just changing the volume. And so this equation, the dilution equation, allows us to calculate the new diluted concentration of any solution. So the whole idea here, it's your initial concentration, so typically the more concentrated one. So you start with that concentration, you multiply it by the volume of that initial solution. That is equal to the diluted concentration times the volume of that final diluted concentration. So in high school, if you heard the term M1V1 equals M2V2, that the M Big M means molarity. But the beauty about this equation, how I have it written here, you can use any concentration unit for C, or you can use molarity, you can use percent by mass, you can use percent by volume, you can use percent mass over volume, it doesn't matter. C just means concentration. But the trick here is whatever the unit of C1 is, you have to also have the same unit as C2. So if you have molarity units, they both have to match on each side. If you're using percent mass concentration units, again, they have to match on each side. So you can use whatever concentration unit you want. They just have to match. And then the same idea here. Concentration units need to match. Volume units need to match on each side as well. So when you're using this equation, if you measure your concentrated stock in milliliters, if you go ahead and calculate V2 or your V final, that will also be in milliliters. So those units have to match in order for this equation to work. All right, so let's do a sample problem. So how I approach these questions is I go through and read them. It's a lot of reading comprehension. We read through them and think, okay, what value is C1, what is C2, what is C1, what is C2, what is V1, what is V2? So if we read through this question, it says, how would you prepare 500 milliliters of a 5% glucose solution from a 25% stock solution? So my idea here is that C1 and V1, these are always the concentrated values, and C2, V2, these are your diluted values. So this might help you kind of go along. So here, if we look at these concentration values, which one is probably C1, the concentrated concentration? 5 or 25? 5. So I like to, oh wait, no, it's not 5. The concentrated value, which one is more concentrated, 5 or 25? 25. So just because that one said last doesn't mean it's C1. Or sorry, doesn't mean it's C2. So in this case, 25, that's our stock solution. Also, it's the concentrated solution. This is C1. And so if we look at the other values given, 500 milliliters of a 5% concentration, this to me sounds like V2 and C2. This is my diluted solution. I'm trying to figure out how much volume of the stock solution do I need to start with. So kind of the only thing that's missing here is V1. Do we see that? So we know C1, we know C2 and V2, we actually don't know what V1 is. So now at this point it's just plug and chug. Okay? So let's put in those numbers. So C1 is 25%. We are calculating for V1. C2 is 5%, and V2 is 500 milliliters. Right? And so then we solve for V1. So without even doing the calculation, what is the unit of V1? What's going to come out as the unit of V1? Milliliters, yes, because V2 is in milliliters. So that answer is 100 milliliters. So 2 sig figs. There, 2 sig figs. So now the question is, it says, how would you prepare this solution? So kind of if you were in lab and you went through the steps here, what this is saying is that you need to start with 100 milliliters of your stock solution, which we said is 25% glucose in this case. So what that means is we would put 100 milliliters of this stock solution, 25% glucose, into a volumetric flask. Then we would dilute that whole flask, the whole thing, to what's the final volume? 500. We would dilute the whole thing to 500 milliliters. And what that means, once we add that water, all that water, so in this case we're adding about 400 milliliters of water, and mix that whole thing up, that whole diluted mixture will have a concentration of what? 5%. So that's how that works, all right? Okay, let's do another one. Oh, this is a good one. Okay, so 50 milliliters of a 3.6 molarity NaCl concentration is added to 100 milliliters of water. What is the concentration of the sodium chloride solution in molarity? Report to 2 sig fig. So I'll give you a couple minutes to do this one on your own, and then we'll come back and get the answer. So this is just, C1 V1 equals C2 V2, but I'm going to point out, be very careful. Be very careful. Reading comprehension. Okay. Are we still working? No. Okay. Who thinks it's A? Who thinks it's B? Who thinks it's C? Who thinks it's D? Okay. All right, so I see a lot of answers. Well, no one really said it was C, which is good. Because C, it's the same concentration. It wouldn't have changed. Okay, so let's walk through this, all right? So just like in the previous question, I like to go through all of the values given and identify, okay, what's C1, what's C2, what's V1, what's V2. So talking about going through these numbers. So it looks like we're starting with 50 milliliters of a 3.5 molarity solution. And we're adding it to 200 milliliters of water. Sometimes drawing it might be useful. Okay, so we start with like 50 milliliters, right, of our 3.6, and we're adding water to it. All right, whoops, okay. So in this case, 50 milliliters is V, the volume. Specifically, it's V1. Because 3.6, that's our concentrated solution, so I'm going to call that C1 in this case. All right, so now the idea is, okay, what are we diluting it to? Again, reading comprehension. So we're adding 200 milliliters of water. So let's go back to our picture. We already have what volume in the container already? 50. So if we add 200 milliliters, what's the total volume? 250 milliliters. So we just added 200. So now V2 equals 250 milliliters. All right, so we have 3 values now, and we just have 1 unknown. What variable in our equation are we actually calculating? C2 in this case. So now it's just plug and chug. So C1 is 3.6 molarity, V1 is 50 milliliters, equals C2, that's what we're calculating, and V2 is 250 milliliters. All right, and so if you do that, C2 is equal to 0.72 molarity. So the answer, I think, is it? Yes? Okay, good. Okay, it's B. So let's just go through some of these answers. So A, which a lot of you thought it was A, You got A when you used V2 equals 200. So you just took into account, but did I trick you? See, I tricked you. Yeah, sorry. All right. But getting it wrong helps you learn, right? Okay, all right. So yeah, and V2 is actually 250 milliliters. So how the wording can change, all right, is if I said we took 50 milliliters of the stock and diluted it to a total volume of 200 milliliters. That's how the wording would change if I wanted V2 to be 200, yeah. Oh, our variable, what we don't have is C2. So I just moved I multiplied 3.6 times 50 and then divided by 250. So I skipped those maths. I'm assuming you know how to do that math? Yeah, okay, all right. Yeah, so sometimes, usually I do this. I usually highlight what I'm calculating, what my variable is. So I'm calculating C2. So I'm like isolating that. That's what I'm calculating for. But I'm just being lazy right now. All right, so yeah, C2 is 0.72. All right, so yeah, how the question could be reworded if we wanted V2 to actually be 200 is if I said 50 milliliters of the stock was diluted to a total volume of 200. Okay, so that's if you did 200 milliliters for A. B is the right answer. C, it can't be C, right? Because we're adding water, we're diluting it. What C implies is that the concentration didn't change. That's weird. And then D, can it be D? No, if we use our intuition, like I think numerically I just kind of like multiplied the numbers together or something to just come up with other answers. Using our intuition, we know when we add water to something, we dilute it, right? So then the concentration should go down. So in doing that, using your intuition a little bit and knowing, hey, when we dilute something, the concentration should go down, we should be able to eliminate D. Good? All right, so that's dilution. And note here, so in this example, we used molarity as our concentration unit. And that's why it's concentration. They just have to match in this case. And in our previous question, we used percent mass over volume. The equation still works in this case. Okay, so finishing up. All right, so it's, this is a lot of definitions. No more math, if that makes you happy. So we're talking about concentrations in our bodies. I already kind of gave you guys a glimpse of this, but we are just big salt bags. We're just filled with salt and sugar, our bodies. And so how a lot of processes occur in our bodies is based upon the concentrations of solute, salt, sugar in our bodies. So the whole idea of osmosis is this idea that water can travel through semi-permeable membranes, such as our cells. Our cells can are basically semi-permeable membranes, meaning that water can go through these membranes, but solute particles typically cannot. All right, so this is kind of a behavior of water. Water will always travel through a semi-permeable membrane to make the concentrations of solute equal on both sides of that membrane. That's the whole idea of osmosis. Water will move into the direction that makes it so concentrations of your solutes are the same concentration on each side. So yeah, osmosis, solvent goes across a semi-permeable membrane. Usually we are talking about water in this case. And this whole idea, water moves across the membrane to create a isotonic system. That's the same, it's a synonym for what I just said. Same solute concentration on either side of the membrane. Same solute concentration on both sides of the membrane. That's the whole idea. Water will move in such a direction to make the concentrations the same on either side of the membrane. And that means isotonic solution, same concentration. Iso means same. And we'll look at scenarios where they're not the same and what happens. Okay, yeah, so that's the picture here. Water molecules are really, really small. So they can pass through these membranes, but solute particles are fairly large. So they stay on their opposite side. So what water is now the force here that's acting to make that isotonic system. All right, so here's an example. We have a solution, so a container two containers separated by a semi-permeable membrane. I have two different concentrations of starch. So starch is the solute in this case. Which way will water flow to create an isotonic system? So this system is going to undergo osmosis. Water is going to move, but we need to predict in which way will water move. This is tricky, and I think students, they often think of it, they think of the wrong way. So take a second and think about it. Which way do you think water needs to move to make an isotonic system? So our goal here is to get the same concentration of starch on either side. Which way does water have to move? Talk about it with someone. Or do you have a question? Okay, you know. Okay. Oh, also the answer is on the next slide. So if you want to check. Which way will water move? And note here, yes, the starch molecules cannot go through the membrane, only water. Okay, which way will starch move? Will it move? Well, why don't we just point? Which way? 1, 2, 3, go. Yeah, water is going to move this way, all right, towards the higher concentration side. I know it's weird. It's weird. Water is moving towards like the larger number. I don't know. You'd think that it would go to the smaller number, right? And that's why I say that there's oftentimes a misconception here. But let me break it down for you. So right now we have the same volume on each side. So the answer is this way. It's going to go this way. H2O is going to go that way. Let's think about it. If we have the same volume of starch on each side of that solution, which side of the container contains more starch molecules? The one on the right, thank you. On the right. So it's more concentrated, right? So we need to dilute the more concentrated side so it matches the less dilute other side. Does that make sense? So that means water has to go that way. Okay, and it's weird because the water is going towards, I don't know, the higher number. To me, that's like counterintuitive. But yeah, the whole idea is we're going to dilute the higher concentration starch side so it matches the other side. Because what happens when water moves that way, we are diluting this side, but what are we doing to the left side? We're removing water, right? So will the concentration, that 4%, will it go down or will it go up? That concentration will go up. The one on the right, thank you, will go down, and then essentially they'll meet in the middle somewhere, like around 7%, right? And that's what's going to happen. So if water goes to this side, the volume level will also increase. The volume level will decrease on the 4% side. So just kind of, showing a picture here, the new container will look something like this, and it'll be about 7% on each side. It'll look like that. Okay, and I think I have that on the next slide. That's what it looks like. So once we've achieved this picture where we've allowed the system to become isotonic, do we see how this is isotonic? Right, 7% on both sides. Once we have the isotonic system, it doesn't mean that water stops moving. It just means that water, there's no net movement of water anymore. So water is still passing through the membrane, but at equal rates in each direction. What does that kind of sound like? Equilibrium, right? Yeah, so you have water passing, going through the membrane, but at equal rates on each side. Right? And so this is your isotonic system. So once you've reached your isotonic system, water's still moving, but just there's no net change. Okay, so that's osmosis. So why does osmosis occur? It has to do with osmotic pressure of solutions. And so I think the big idea here is that osmotic pressure increases for a solution as concentration increases. If there's one thing you pull away from osmotic pressure is this idea. Osmotic pressure of a solution increases as concentration increases. Concentration. This is why water moves. Undergoes osmosis through a semi-permeable membrane. So this idea, osmotic pressure, if I go back to this picture, this one up here, which side of the container exerts a higher osmotic pressure? The 4% or the 10%? Let's go back to the definition, or the thing. So osmotic pressure increases when concentration increases. So which side has more osmotic pressure? The 10%, because it's more concentrated. So what osmotic pressure is we know if we opened up this semi-permeable membrane, which way would water go? It would go this way, right? And the water level would go up on that side. What osmotic pressure is if we wanted to stop this osmotic pressure, if we wanted to stop that process, if we wanted to stop water from moving this way, we would have to exert a pressure on the concentrated side to make that not happen. That's what osmotic pressure is. So that's why the more concentrated solution exerts a higher osmotic pressure, which is kind of a weird way of thinking about that. But really the big takeaway here with osmotic pressure is that it increases with increased concentration. Okay, so, and I think I say that right here. More concentrated the solution, higher osmotic pressure. A lot of the systems in our bodies, it's dependent on the idea that our different systems are exerting similar osmotic pressures, so we don't have a mass movement of water going from one place to another, because that can cause a lot of different health problems, bloating, what have you. We want to make sure osmotic pressures of the solutions in our body remain somewhat the same. Okay, so last idea here kind of concerning osmotic pressure, osmosis, is back to the idea of isotonic solutions. We need to make sure that like our blood, the blood plasma in our body is isotonic with like our cells in our bodies as well. Because what happens is when we have this imbalance of salt concentrations, water, a lot of osmosis will happen naturally, and water will go in or out of your cells, and bad things can happen. So we want to make sure that our blood plasma is isotonic with the cells within our body. So in our human bodies, this is what is isotonic with red blood cells. So our blood plasma is about 5% glucose and 0.9% salt. So that's what we call a saline solution. Okay, so if you look up a saline solution, if you use that for, I don't know, like your nose or eye irrigation or something, it's like 1% sodium chloride. All right, and that's why, like, if you ever get tap water in your eye, okay, tap water, there's like no salt in tap water, and it burns your eyes, right? Because it's not isotonic. Tap water is not isotonic with your bodies. But if you use something like, you know, if you have like contact solution or something, and you use that to wash your eye, it doesn't burn, right? Because they are saline solutions, and they are in equilibrium. They're the same concentration as our bodies. That's why they don't burn. So that's saline solutions. Okay, so keep those concentrations in mind. When we introduce solutions that are the same concentration as these, osmosis in one net direction won't happen, that we have this nice equilibrium. But what happens when we don't have the same concentration with like our red blood cells, so hypotonic solutions are just solutions that are less concentrated than those concentrated. All right, less concentrated than what we just described, those two concentrations. Hypertonic solutions are more concentrated. Isotonic solutions, they are the same concentration. We already talked about those. So this is what a red blood cell looks like in an isotonic solution. Same concentration on the inside as the outside. So let's Let's draw that. So it's like 0.9% on the inside, 0.9% sodium chloride on the outside. So you have this like water going in and out at equal rates. So let's think about putting a red blood cell, which is usually 0.9%, into a hypotonic solution. So it's less concentrated. So let's say we put it into a solution that's 1.1% salt. So that same idea with the starch solution, if you have two bodies separated by a semipermeable membrane, which way will water go? To this way or into the cell? Into the cell, because it's more concentrated, that there's more water on the outside, so it's going to try to dilute the cell on the inside. So when you put a cell into a hypotonic solution, the cell, the red blood cell swells up with water and it explodes. This is called lysis. Yes, lysis, or hemolysis, but lysis for short just means like explode or breaks in this case. So water will go into the cell versus a hypertonic solution. So again, let's say that the red blood cell is 0.9%, the outside, let's say it's 2% salt. So again, like the starch example, which way will water go to make isotonic solutions, so the same concentration on each side? Water is going to go out. It's going to try to dilute, the cell is going to try to dilute the more concentrated outside. So this is called crenation. The cell loses all its water. All right, so water goes out in this case. All right, so there we go. So these ideas, how a cell behaves based upon what type of solution you put into it, is definitely a learning objective here, and understanding what does hypo and hypertonic mean. All right, so, I think these are the same pictures here. So yeah, hypotonic, water goes into the cell, it swells up. Hypertonic, the water in the cell leaves, tries to dilute the more concentrated outside, and your cells shrivel up. Okay, and then this is normal. That's in an isotonic solution, which I think is pretty interesting. Okay, and this whole idea is why you can't drink salt water. Let's think about it. Salt water. Do we think that just, like, don't think about it too hard. Do we think salt water is hypertonic or hypotonic? Hyper, yeah, there's tons of salt in salt water, right? So if we put really, really salty solutions inside our body and drink it, we're making our body a hypertonic solution. So in hypertonic solutions, water is going to leave our cells. And this is why drinking salt water actually dehydrates you. Right? You'd think just drinking water would hydrate you, but no, salt water will dehydrate you because water is leaving your cells. Your cells are going to shrivel up and undergo crenation in this case. So yeah, it draws water out of your cells. Okay, we got 8 minutes. Yeah, we can finish. Yeah, so seawater is hypertonic. Okay, so we talked about diffusion of small molecules like water. Okay, water can undergo osmosis through a semipermeable membrane. All substances can undergo mass movement. We call this diffusion. So it's the idea, like with gases, if I spray, perfume in the corner of the room, eventually everyone's going to smell it, right? Because the gas particles are going to move across the room, given enough time. So all molecules do undergo diffusion at a certain point, just like water, things that are dissolved in water as well, given enough time. All molecules will diffuse and become uniform. So like here, if you put a drop of green food coloring, given enough time, even if you don't mix it, it will all become uniform and green within there. So how this kind of relates to the medical field is dialysis. The whole idea of dialysis is you take the blood out of your patient and dialysis is essentially an artificial kidney. When your kidneys no longer function, your kidneys is what takes out toxins out of your blood. So when a person can't do that anymore, we do it artificially, where we take the blood out of the patient and we run it through this column where the solution, the blood that you're running it through, is isotonic with this other solution. So the blood, it's running through an isotonic solution. So what happens is those small toxins within your blood will just naturally diffuse into an area of lower concentration that you see here. right? So all molecules will undergo diffusion in that case. So sometimes you have to run multiple dialysis cycles to try to get all those toxins out if there's a lot of them. And then hopefully once it runs through that isotonic solution, when it goes back into the patient, you're essentially recycling it back into the patient, it no longer has those toxins after they've diffused out of the dialysis bag. So here, the urea and other waste products, we will call those toxins. So this happens essentially through diffusion. Diffusion. All right, so the idea that we can move molecules in dialysis, water through semi-permeable membranes, but our cells also move molecules and molecules in and out of the cell. The cell needs to decide, okay, I need more sodium ions, I need more glucose molecules. So how does a cell do that? So remember, cells are made up of phospholipid bilayers, remember? So you have this bilayer where it's polar on the outside, but polar on the outside and nonpolar on the inside. So you have this like protective sheet around a cell. So a cell has come up with ways to be able to transport different types of molecules, depending on what the structure of that molecule is. So here we have 3 different ways that cells can transport molecules in and out of it. So there's 3 different ways. We call passive or diffusion, passive diffusion type of transport. Really, it's just regular diffusion. Another is called facilitated transport, and the last one is active transport. So I'll go into the details of all of these. The first one, passive diffusion, is for really small molecules. Typically, they're nonpolar. So what passive diffusion is just regular diffusion. That we have these really small molecules that can just pass right through the phospholipid bilayer. It can like just wriggle its way in through it, okay, through that bilayer. So things like oxygen, CO2, nitrogen, all those things can just wriggle itself inside, past the phospholipid bilayer, through the active diffusion. And diffusion just happens naturally over time. So that's this picture right here. See how it's just like wriggling through? It's just going right through? So these are for really small molecules. Typically, they are nonpolar. The next one is facilitated transport. These are really important for polar molecules or ionic substances, so something like sodium plus. So these are bigger molecules. They cannot wriggle through the phospholipid bilayer, so the cell has to kind of just make a channel for it because the molecule's too big. All right, so once you have a channel, then you can kind of allow molecules to go through that channel if, let's say you're moving a glucose molecule from a high concentration to a low concentration. That will happen naturally through diffusion. But you need the channel to do it. So that's called facilitative transport, where you have a channel. Diffusion will allow those glucose molecules to pass right through. Then the last type of transport is active transport. It still uses a channel. Okay, we can still move polar molecules or ionic molecules, but here's the difference. You are moving like a glucose molecule from a low concentration to a high concentration. That cannot happen naturally. You have to give the cell energy or the channel process energy in order to push one of those molecules against a concentration gradient. That's what we call it. So you're trying to push like sugar from low concentration to high concentration. That's harder to do, so you have to give it energy. So the last 2 are related to one another, right? Facilitated transport, active transport, but only one of them requires energy. Which one requires energy? Active, and that's when you're pushing a molecule to somewhere that has more concentration, which does not happen naturally. So yeah, we're done with chapter 8. Okay, so good. So homework's due on Sunday. I still have office hours today if you want to hang out.